So now we are going to continue our chemical bonds discussion. This time we're going to look at covalent bonding and writing Lewis structures to show us where those bonds occur. Nonmetals desire to take electrons to form full valence shells. Okay, they're going to be more electrically stable if they have the same valence shell as a noble gas. So again, this is the ideal, having a filled shell. When no metal is present to donate electrons, the plan B, like the secondary okay it'll work option, is our nonmetals can share their electrons. They can, in that case, they can obtain a full valence shell even though it's only a partial shell. So what we're looking at there would be, for example, a hydrogen is going to come across another hydrogen. Neither of them are stable, neither of them are happy as they are, but what they can do is each can donate one electron to the other. So this hydrogen now allows its electron to be used by the other hydrogen, and this hydrogen allows its electron to be used by the other hydrogen. So some of the time the two electrons will be closer to this nucleus, and at other times they're closer to this nucleus. But in either case, it's more electrically stable in this bound position. In order for us to really understand the positioning of our bonds, what we can do is draw Lewis dot structures. A Lewis dot structure essentially is going to show you dots as free electrons and then lines that indicate the bonded pair of electrons. So I'm going to begin with a sample molecule. I'm going to use PCl3 here. Okay, so my phosphorus trichloride, the process involves adding up your total number of valence electrons that you have in the compound. So we look at phosphorus, and we find phosphorus has 5 valence electrons. It's in group 5A. And we find that chlorine has 7. However, there are 3 chlorines, so we must multiply it by 3. That gives you a 21. Add to that 21 the 5 from phosphorus, and we have a total of 26. Now, it's very important, you have to keep in mind, you need to keep track of the number. As you start filling in electrons in the structure, you're going to subtract those from here. So our second step is you need to identify the central atom. The central atom is our least electronegative non-hydrogen. Now this is important. Hydrogen only has 1 valence electron, so it's not going to make a good central hub of these covalent bonds that have to take place. So the least electronegative non-hydrogen, if I compare these two, we think back to our general trend. We know that on the periodic table, electronegativity increases from the bottom left to the top right, stopping at fluorine. So we consider that chlorine is here, phosphorus found here. We know that phosphorus would be the less electronegative of the two. So I will start by drawing in my phosphorus as a central atom. Chlorines are going to flank it on both sides, and a third chlorine down on the bottom. Now, as part of this step, once we've identified the central atom, we're going to begin placing electrons by connecting single bonds to that central atom from the outer atoms. So to this central atom, I'm going to take 1, 2, 3 bonds. Each bond houses 2 electrons. So we're going to have 3 times 2 is 6 electrons that we just placed. Subtract those from our total, and we're left with 20 electrons. Now we want to fill in dots to complete the outer atom octets. Currently this chlorine has only 2 electrons, so it needs 6 more in order to have its full octet. So I'll place those 1, 2, 3, 4, 5, and 6. So I'll subtract those out, and I see I still have 14 remaining. I'm going to have enough to fill both of these, so let's go ahead and just do them all. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll take these 12 away, and now I'm left with 2 electrons. Once we've done that, we now need to fill the dots in to represent electrons to make this central atom's octet full. Currently, the phosphorus has 2, 4, 6. We're going to add 7, 8. That gets rid of the rest of our electrons, and now we're good. So we give you a different example now. It doesn't always work out that we can have this clean single bonds everywhere thing. What we're going to do is we're going to look at a different example where we're going to have to figure out multiple bonds. I'm going to give you hydrogen cyanide, HCN. We're going to again find the total valence electrons. Hydrogen has 1, carbon has 4, nitrogen has 5, for a total of 10 valence electrons here. I'm going to begin by looking again for the central atom, the least electronegative atom that is not hydrogen. So hydrogen's out. Between carbon and nitrogen, we find carbon and nitrogen in the same group. Carbon is to the left of the nitrogen, so it is the less electronegative. So we start with our carbon, flank it with hydrogen and nitrogen on its sides, and then we're going to draw in those single bonds. So I have 2 single bonds, that's 4 electrons placed, subtract it from your total, and we're left with 6. Now we want to fill dots to complete our outer atom octets. So here with hydrogen, we notice it has 2 valence electrons. Because hydrogen is in the very first energy level, it only needs 2 electrons to have a full octet. So this hydrogen is fine. Now we look to the nitrogen, we see that it currently has 2 electrons in a bond. So we're going to fill its octet with 3, 4, 5, 6, and now 7, 8 electrons. The nitrogen's good. We'll subtract those 6 from our total, and we now have no extra electrons to place. So the issue that we find is that the carbon only has access to 4 electrons. To solve this problem, if you've run out of electrons before the central atom is filled, you can take the paired electrons from one of the outer octets. What we'll do is we'll take these 2 and we can share them in a bond with carbon. So we'll take these 2, bring them over, and now they're not just 2 for nitrogen, they're 2 for nitrogen and they're shared with carbon. Nitrogen still has 8, carbon now has 2, 4, 6, so we'll repeat the process here, make another bond, cancel those, and our final Lewis structure shows hydrogen, carbon, nitrogen. Now, let's work out a couple practice problems. Which bond forms when nonmetals share electrons? So the bond that forms when 2 nonmetals share is known as a covalent bond. Why do nonmetals share electrons? They share electrons to fill their valence shell. At least some of the time. Why does a Lewis structure help us to see, what does a Lewis structure help us to see? Lewis structures enable us to see the bonds and paired electrons. Now we're going to write Lewis structures for each of the following. We're going to begin here with O2. So oxygen has 6 valence electrons times 2 gives you a total of 12. Since we don't have a difference in electronegativity, we don't have a central atom, we'll write the 2 together. Now connect this single bond and subtract those 2 electrons. We're left with 10. We're going to now fill the outer shells of each. So I've got 1, 2, 3, 4, 5, 6, and 8. I'll take those 6 away and I'm left with only 4. So this presents a problem. I can only fill 4 on this oxygen, and that leaves it with 6. So we're going to have to take these 2 electrons and form a double bond. So our oxygen is going to have 2 electron pairs, so 2 lone pairs and 2 shared pairs. Now looking at CH4, we'll do the same process. Carbon has 4 valence electrons, hydrogen has 1, times 4 is 4, for a total of 8. Carbon is the only non-hydrogen, so it's the central atom. We are going to take those 4 hydrogens, place them at 4 ends of the carbon, and add these covalent bonds. Each covalent bond takes 2 electrons, so that's 2, 4, 6, 8. Take your 8 away, and we're done. Now we can check. Each hydrogen just needs 2 electrons, so that single bond takes care of every hydrogen. The carbon has 2, 4, 6, 8, and everyone's good. Now, the nitrogen and fluorine. Nitrogen has 5 valence electrons. Fluorine has 7 times 3 to give 21, and a total of 26. Nitrogen is less electronegative than fluorine, so that makes it our central atom. And we will have our fluorines here, here, and here. We'll combine, or we will join these with covalent bonds, and we get 2, 4, 6, so take those 6 away. Leaves us with 20. Fill our outer atoms to have full octets. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Take those 18 away. I'm left with 2. Now fill the central atom. I have 2, 4, 6, and I can finish it with 7, 8. SO4. We now have SO4, and this is new. We have an extra charge. This is a polyatomic anion. The way this works is when totaling your valence electrons, we'll have to include whatever the negative charge is as additional electrons. So my sulfur has 6 valence electrons. Oxygen has 6 times 4 gives 24. And then I have a charge of 2 minus, which comes from 2 additional electrons that I add to our valence pool. So that's 6 and 24 plus 2 makes 32. Now I have a central sulfur. Outside the sulfur I have 4 oxygens, 1, 2, 3, and 4, which I will attach single covalent bonds to. So that's 2, 4, 6, 8 electrons being used. When I subtract out these 8, it leaves us with 24 electrons. I'll now add those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Everybody's happy, even the sulfur in the middle, because it already has 4 pairs for a total of 8.